Hello all, so let's continue with further topic, and the topic is average mutual information. Now we already seen this mutual information, right? This is mutual information. This is from where we started, right? And this is given by this. So here in case of mutual information, as you can see that it is just for one possible outcome. That is for random variable x equals to xi, that is one possible outcome, and for y equals to yj. Now, what if we have several possible outcomes? So, for several possible outcomes, right? So, the average mutual information between, so now we won't be considering a single possible outcome of a random variable x and y, but we will be considering the several possible outcomes between x and y. So, now we will be writing the average mutual information as I of x, y, right? So, this is for the several possible outcomes, and since we are averaging, so we know that we have to just do the weighted sum. That is, let's say I again range from 1 to n and j from 1 to n, as we already know this, and we know we have to weight our mutual information. So this is our mutual information. Let me draw the boundary in here. So yeah, so this is mutual information, and we have to weight this. So we are just taking the probability of xi comma yj. So now what is xi comma yj and why it is needed? So this xi comma yj is the joint occurrence of xi and yj. That is probability of, in other terms we can write xi intersection yj, that is both happening at a time. So just what we are doing for averaging is that we are taking our mutual information, we are weighting, we are just multiplying, or we can say weighing it with the probability of joint occurrence of both the events, and we are just taking summation over all possible outcomes of random variable x and random variable y, right? Now let's further simplify it. So please mind the notation. Now we are writing capital X and capital Y. So again it's summation. I'm just substituting the value of the mutual information. So P of xi yj is as it is, and I'm just substituting. We know the formula that xi yj. I'm just modifying it directly now, just keeping one step. Initially is like this. Okay, I am just multiplying above and below by yi, and the above term can be written as this, that is this thing, that is joint occurrence. So just I wrote like this. Now what we can do, we can further simplify it, or it's not needed, right? Let's say I'm just keeping it like this, and let's see some properties of this thing. So now let's see the properties. So first property is that when obviously x of, that is I of, is 0, when this will be 0, when x and y are statistically independent. Very fundamental property. And this will happen on when this log argument will be 1, and when this will be 1, this will be 1 when we know that when x and y are statistically independent, then we can write the joint occurrence as the probability of individual occurrence, right? So numerator and denominator will be same and get cancelled, and that's why we are getting 0. And this we already know that when they are independent there is no information, right? The mutual information is 0. So again the average mutual information will also be 0. Easy. And second is that the average mutual information is always positive, and so, and 0 of course when, in this case, property number 1, that is when x and y are statistically independent, right? And this is always positive. And the third property is that these properties are not that much important, but just I am writing so that I can cover everything, is always less than or equals to minimum of xi and yj. This is not exact xi, this is symbol. Okay, so or alphabet we can say. So this is some other symbol of xi. Let someone write like this xi, and yj also something like this. Okay, so pardon me for my symbols. So this is nothing but size of the alphabets. Now we are going to very important term which is called the entropy, and it is derived from this only, that is our average mutual information. So this is the definition of our average mutual information. When we will take average self information, then it is nothing but entropy, and that's why I started from average mutual information, so that we can uh, arrive through this topic which is very important called entropy. So what is entropy? So average self information is nothing but entropy, is equals to entropy, and we already know it is denoted by h of x, and we know that when it is just dependent on x, all the terms of y will be gone, right? That is the probability that the probability of occurrence of event y equals to yj uniquely determines the probability of occurrence of event the x equals to xi, right? So we can just write it as probability of xi and I of xi, that's it. Okay, so in this you can see just xi term, and here it is nothing but I of x comma xi comma yj. Here we will write just, let me show you the previous, yeah. So here we will just write the xi p of xi, and here we will just write I of xi, that's it. And this will give us, and we will just take the average across now this point, because this is gone, nothing of y is there, just self information. That's why self with x with itself, y with itself, like that. So this is nothing but our entropy, and this is a very important topic. Okay, and we already know, you might be familiar with all this stuff from your previous bachelor's knowledge, undergraduate knowledge, and we can write I of x, we already know, like this. So this is very important formula, that randomness. Okay, we already know what entropy means. So what is the randomness associated with x, random variable x, can be characterized mathematically by this entropy, and it is given by the probability of that xi, and just multiplied with log to the base 2 inverse of that probability, and we are weighting across all the possible xi's, and we know that our I is ranging from 1 to n, right? So what is x now, where x represents, let me write all the stuff, where x represents the alphabets of possible output letters from a source, and h of x represents the average self information per letter or per source letter. Now again we are considering one special case, that when letters are equiprobable. Okay, so when all the outcomes from the source are equiprobable, and we know we have n outcomes, so probability of each outcome xi will be 1 by n for all I belongs to 1 to n. So we can simply write h of x as summation I is from 1 to n, 1 upon n log to the base to 1 upon 1 upon n, which is nothing but summation, I'm going a little bit fast, log to the base to n, right? And we know that this is independent of I, so we can just write it is outside log to the base to n, and we know summation of I equals 1 to n will be n, So this n and n will get cancelled, and at the end we are just left with log to the base 2n. So this is very simple. Now it's very simply reduced to a very small and neat formula in case of equiprobable case, that our randomness associated is nothing but just take log to the base 2 of total number of outcomes. That's it. Okay, and in general, this you can prove as well, that in general the maximum value of entropy will be always less than or equals to this. That is, we will get maximum randomness when we are having the outcomes of the source equiprobable. Okay, and the example let's consider, and let's plot one graph. So the example is that, let's say we have one source and it emits the statistically independent outcomes or letters. Outcomes. Let's say it is binary source where each output letter can be either 0 or 1. Okay, and the probability of occurrence, that is the 0 will occur with probability q. So obviously 1 will occur with probability 1 minus q, because total probability is 1, right? So how we can write h of x now for this source? Simply q into ln of 1 by q and plus 1 minus q into ln of 1 upon 1 minus q. Simple. And this is nothing but minus q ln q minus 1 minus q ln 1 minus q. Okay, mind it, this is log to the base 2. Okay, so to the base 2, not ln. Let me write log to the base 2, it will be better. And if you will plot this we are already familiar with, that let's plot h of q. As you can see, this is only dependent on the probability value, that is q, and it is given by something like this, that so it will be maximum when q is 0.5. okay, that is our outcomes are equiprobable. Then you can verify by placing value of q as 0. So we will get 0 and place 0. Okay, and when it will be 1, then also 0, because log 1 is 0, right? So this way you can verify that we are getting this thing, that is maxima, and it will be 1 down here at 0.5. You can just put 0.5 and you will get answer as 1, right? Now similar to this entropy, okay, there is also something called conditional entropy, and this is also the same thing, that conditional entropy, and it is given by h of x given y will be equal to summation of I equals 1 to n, j equals 1 to m, the joint probability, and log to the base 2. Now we will take the conditional probability, that is xi given yj, because we are having x given y. That's it. Okay, so you can compare that previously what we were having just p of xi, but there we are just having the self information, average self information, or we can say entropy. Now it's conditional one, right? So that's why here the conditional probability. That's it. Now what this indicates, right? So let me write the sentence that h of xy, x given y, is the information, or we can say the uncertainty in x after y is observed. That is, let's say we are observing some event y, right? So after observing event y, what is the information or uncertainty that is there in x, or what is the randomness in event x, is given by this mathematical formula, which is nothing but conditional entropy, right? Now again, the average mutual information from where we started, that is we started with just mutual information, but we just derived average mutual information as well in the very beginning of this lecture. So average information, we can write it like this: h of x minus h of x given y. Now you might wonder how. Let me just prove it. This is very important, okay? The proof is that we know our average mutual information is given by summation I equals 1 to n, j equals 1 to m, the joint occurrence of both, log to the base 2, probability of xi given yj. This is where from we started with in our beginning of this lecture, okay? So this thing we already know. Now we are just splitting the logarithm by just using logarithm formula. So minus I am taking outside, and you can see this I can write it as p of xi yj as it is, log to the base 2 1 upon p of xi yj. Just I am writing this term, you can see here, as 1 upon, and that's why we are having negative down here. And the second term, again summations p of xi yj, and just writing this as it is, p of xi. This is just a property of log that we are using, right? And now if you can observe this thing along with the minus sign I'm taking, okay, it can be written as minus h of x given y. This we already saw in our last slide, right? This thing, and this thing we already know is nothing but just h of x. So we can write in conclusion this thing. This I already wrote it, right? I'm just not writing it again. So we can write this thing, right? So, and clearly it will be positive when the entropy will be greater than the conditional entropy, right? And it will be zero, right, when this will be zero when both are equal. So I hope things are getting clear. Since the lecture is little bit bigger, I'll show you in the next lecture that what this actual h of x given y and h of x means by drawing one block diagram, okay, of input and output of the channel, right? So stay tuned. Thank you.